The conference room deep beneath Whitehall carried the stale air of 1,000 wartime meetings. Cigarette smoke hung in layers beneath the electric lights, and the leather chairs around the mahogany table bore the worn impressions of men who spent their days planning the impossible. On that particular morning, in late May 1942, Admiral Louis Mountbatten stood at the head of the table, his hands resting on a stack of technical drawings that would have seemed like fantasy to anyone outside that room. The assembled officers represented the cream of British military planning. Naval commanders with decades of experience, army engineers who had built bridges across 4 continents, logistics specialists who could calculate tonnage requirements in their sleep. They were practical men, rooted in the realities of warfare as it had been practiced since ancient times, which perhaps explains why Mountbatten's next words struck them as utterly absurd. The Admiral spoke with deliberate calm, as though proposing something entirely reasonable. Since we cannot capture a port, we shall need to construct one and bring it with us. We will build it in sections in England, tow it across the Channel, and assemble it on the beaches of France. Within days of landing, we will have harbour facilities equivalent to Dover. Silence held for perhaps 3 seconds. Then someone began to laugh. Within moments, the room erupted. Officers who normally maintained rigid military decorum doubled over with mirth. One general slapped the table hard enough to rattle the teacups. A rear admiral wiped tears from his eyes. The very notion defied everything these men knew about naval architecture, about the violence of Channel storms, about the weight of concrete and the fury of German artillery. Yet Mountbatten did not laugh. He waited, expression neutral, until the hilarity subsided into embarrassed coughing. Then he continued, as though the interruption had not occurred. The Prime Minister has directed that this be done. The difficulties will argue for themselves, but they will be overcome. We begin immediately. The laughter died completely. When Winston Churchill directed that something be done, it would be done, regardless of how many laws of physics needed bending in the process. What none of the men in that room yet understood was that they had just witnessed the birth of the most audacious engineering project of the entire war. Before D-Day arrived 2 years hence, Britain would pour more than 1 million tons of concrete and 70,000 tons of steel into a scheme that conventional wisdom said could never work. 45,000 workers would labour in secret across England, building components for harbours that would not exist until assembled under fire on hostile shores. The mathematics of invasion were about to be rewritten, not through military genius alone, but through the radical notion that if nature had not provided what was needed, human ingenuity would manufacture it from scratch. The immediate problem was simple enough to state, but appeared impossible to solve. Any invasion of occupied Europe would require enormous quantities of supplies landed continuously, regardless of weather. History provided only one proven method for sustaining such an operation: capture a major port. Yet every significant harbour from Norway to Spain now bristled with German defences that made direct assault suicidal. The lesson had been written in blood on the beaches of Dieppe just 3 months earlier. On August 19th, more than 6,000 Allied troops, mostly Canadian, had stormed ashore in a raid meant to test German coastal defences. The result was catastrophic. Machine guns positioned in concrete bunkers carved through wave after wave of attacking infantry. 27 Churchill tanks made it onto the beach. Every single one was destroyed or abandoned. Of nearly 5,000 Canadian soldiers who landed that morning, fewer than half returned to England. Many of those who did return carried wounds that would never fully heal. The butcher's bill from Dieppe staggered even hardened military commanders. Over 900 Canadians died outright. Nearly 2,000 more became prisoners, hauled off to stalags where they would spend the rest of the war behind barbed wire. Royal Navy losses added another 75 dead. The RAF lost 62 aircrew in the skies above the port. German casualties barely exceeded 600. The ratio was roughly 5 Allied casualties for every German defender, and the raid achieved precisely nothing of strategic value. Major General Roberts, who commanded the Canadian division at Dieppe, filed a report that should have ended any thought of directly assaulting a fortified port. The German defences exceeded every estimate intelligence had provided. Concrete casemates housing heavy artillery proved impervious to naval bombardment. Machine gun positions enjoyed overlapping fields of fire that turned the beaches into killing zones. Even if Allied forces had somehow captured Dieppe intact, German counterattacks would have retaken it within 2 days. The port facilities themselves had been prepared for demolition. German engineers could render any captured harbour useless within hours. The strategic contradiction became inescapable. The Allies needed ports to invade Europe. The Germans had fortified every port so thoroughly that capturing one would cost tens of thousands of casualties and might not even succeed. Field Marshal Rommel, appointed to inspect Atlantic defences in late 1943, found the existing fortifications inadequate and immediately ordered their strengthening. His tour of the coast revealed gaps and weaknesses that he set about eliminating with characteristic energy. Rommel's confidential assessment, written for his superiors in Berlin, painted a grim picture of coastal defences as they existed when he arrived. No coherent defensive concept existed. The preparations already in place failed to match the seriousness of the threat. His solution involved transforming the entire coastline into a fortress. Millions of mines were laid across potential landing beaches. Concrete pillboxes sprouted at every tactical position. Beach obstacles designed to rip the bottoms from landing craft were emplaced below the high tide line. Inland, wooden poles with explosive tips dotted every field suitable for glider landings. Most critically for Allied planning, Rommel focused enormous energy on port defences. A secret memorandum he sent to the Führer at the end of 1943 argued that the enemy's main objective would be seizing a port capable of handling large vessels. The German leader designated 11 major ports as fortresses to be defended to the last round and the last man. Dunkirk, Calais, Boulogne, Le Havre, Cherbourg, Saint-Malo, Brest, Lorient, Saint-Nazaire and several others received priority for reinforcement. Each boasted heavy naval guns in concrete emplacements, extensive minefields, dedicated garrisons, and demolition charges planted throughout the docking facilities. The German defensive philosophy rested on an assumption so fundamental that no commander questioned it. Invasion forces required ports. This logic had governed military operations since antiquity. Armies needed harbours for supply ships, cranes for unloading heavy equipment, warehouses for stores, workshops for repairs. No army could survive on open beaches for more than a few days. Weather would scatter the supply vessels, storms would drive ships onto the shore, and the lack of proper docking facilities would create impossible bottlenecks. General Eisenhower, appointed Supreme Commander of Allied forces preparing to invade Europe, understood the paradox with painful clarity. His private diary from March 1943 captures the dilemma in stark terms. The choice appeared impossible: attack heavily fortified ports and accept catastrophic casualties that might destroy the invasion before it properly began, or land on open beaches and watch supply lines collapse within weeks as channel storms scattered the fleet. Either course seemed to lead inevitably to defeat. The alternative that Eisenhower referenced in his diary had begun taking shape even before Dieppe proved how deadly port assaults would be. The concept traced its origins to the First World War, when Churchill, then serving as First Lord of the Admiralty, had proposed using flat-bottomed barges to create temporary harbours for operations against the Dutch coast. That war ended before the scheme could be tested. Churchill never forgot the idea. During a conference in spring 1942, discussions turned to the impossibility of capturing a port. Churchill's response, remembered by everyone present, electrified the room. If capturing a port was impossible, then the solution was obvious: construct one and bring it along. The engineering challenges seemed to multiply with every moment of consideration. Building a harbour capable of handling hundreds of ships would require thousands of tons of materials. Transporting such materials across open water exposed them to storms, mines, and enemy attack. Assembling a harbour under fire seemed like asking men to build a cathedral while being shot at. Anchoring anything to the seabed in waters that rose and fell 20 feet twice daily violated everything harbour engineers understood about construction. Yet strategic necessity left no alternative. On the 30th of May, 1942, Churchill issued a directive to Mountbatten that consisted of just 60 words, but would change the course of the war. Piers for use on beaches must be constructed. They must float up and down with the tide. The anchor problem must be mastered. Let me have the best solution worked out. Do not argue the matter. The difficulties will argue for themselves. Mountbatten assembled the finest engineers Britain could provide: naval architects, harbour construction specialists, hydraulic experts, concrete engineers, all gathered at the Institution of Civil Engineers to tackle what seemed like an impossible assignment. Their initial meetings generated more questions than answers. The sheer scale of what Churchill demanded appeared to violate basic physics. How do you anchor thousands of tons of concrete to a sandy bottom? How do you keep piers stable when the water beneath them rises and falls 20 feet every 12 hours? How do you protect vessels from Atlantic storms without building breakwaters that would take years to construct? The planning staff calculated requirements that seemed designed to induce despair. The artificial harbours would need capacity matching Dover, Britain's busiest channel port. They must handle 12,000 tons of supplies daily in all weather conditions. They must accommodate everything from small landing craft to 10,000-ton merchant ships. They must be operational within days of the invasion. They must survive storms that regularly destroyed permanent harbours. Meeting even one of these requirements would challenge the best engineers in the world. Meeting all of them simultaneously seemed to require magic rather than engineering. A Welsh civil engineer named Hugh Iorris Hughes submitted detailed plans between June and August of 1942 for a floating harbour that incorporated lessons from every harbour construction project of the previous century. Other engineers contributed specialised components. A Royal Engineer Lieutenant named Alan Beckett designed flexible steel roadways that could accommodate tidal variations while supporting fully loaded trucks. Naval architects proposed using obsolete merchant ships as instant breakwaters by sinking them in predetermined positions. The most ambitious element involved massive concrete caissons that could be towed across the channel and sunk to form permanent breakwaters. Testing became essential. The Scottish harbour at Garliston in Wigtown Bay offered characteristics similar to Normandy beaches. The area was flat, sandy, remote, and sparsely populated. A security cordon was established around the entire region. Local residents were evacuated under emergency wartime powers. The whole stretch from Garliston through to the Isle of Withorn became off-limits to civilians. A military camp appeared at Cairnhead to house hundreds of engineers who would spend months testing and refining harbour components. The tests revealed flaws that would have proven catastrophic if discovered only on invasion day. Early floating roadway designs collapsed under the weight of 7-ton trucks when subjected to realistic wave action. Flexible roads made of rolled materials washed away entirely during storms. Various pontoon designs undermined in sandy bottoms, causing bridge spans to fail structurally. Only Beckett's design, which used individual floating sections connected by flexible joints, survived repeated storm testing undamaged. Massive floating breakwaters made from steel and rubberized canvas underwent extensive modification after repeated failures. Original designs used hemp rope to connect individual sections. Testing showed the ropes parted under storm conditions, allowing huge breakwater sections to drift into the inner harbour where they could destroy everything. New steel cable connections with multiple redundant safety systems replaced the rope only after several test failures nearly destroyed the entire test facility. Security surrounding the project approached levels normally reserved for atomic research. The codename Mulberry revealed nothing about the project's actual nature. It was simply the next available name on a list of randomly selected designations. All written communications referred only to Mulberry, never to artificial harbours or floating ports. Workers at construction sites signed Official Secrets Act declarations promising never to discuss their work. Photographs of components were strictly forbidden. Intelligence services monitored conversations in pubs near construction yards, alert for any careless talk that might reach German ears. German aerial reconnaissance posed a constant threat. Luftwaffe planes photographed southern England regularly, searching for evidence of invasion preparations. The Phoenix caissons proved impossible to hide once construction began, as they were simply too massive to conceal. The cover story claimed they were experimental anti-submarine barriers to be deployed in the English Channel. German intelligence apparently accepted this explanation, making no special preparations to counter artificial harbours. An extraordinary security breach nearly exposed the entire operation in May 1944, just weeks before the invasion. The Daily Telegraph crossword puzzle began including words directly related to invasion planning. On consecutive days, clues led to solutions, including the names of all 5 invasion beaches and, most alarmingly, Mulberry itself. Intelligence services immediately investigated the headmaster who compiled the puzzles. Intensive interrogation revealed he often asked students for interesting words to include. Many of those students lived near American military camps where invasion planners worked. The words had entered student vocabulary through overheard conversations and been innocently repeated. Investigators concluded the appearance of classified code names was indeed coincidence, though an unnervingly improbable one. By June 1944, the artificial harbours existed as thousands of individual components scattered across southern England. 2 complete harbours had been constructed. One would support American forces landing at Omaha Beach. The other would support British and Canadian forces at Gold Beach near Arromanches. Each harbour required approximately 600,000 tons of concrete and fabricated steel. Components included 213 Phoenix caissons of various sizes, 10 miles of floating roadways, 33 pierheads, 70 obsolete merchant ships to be sunk as breakwaters, and 24 massive floating outer breakwaters. Moving this artificial fleet required 150 ocean-going tugs, specially modified for long-distance towing. The tugs were marked with large M letters painted on their funnels. Crews took fierce pride in their assignment, understanding they were part of the most ambitious engineering project in military history. Phoenix caissons had to be towed at speeds not exceeding 4 knots to prevent structural damage. The journey from English ports to the Normandy coast would take 2 days under ideal conditions. Weather predictions became absolutely critical. Rough seas could damage delicate components or part tow cables. The tugs had to navigate mine-infested waters while maintaining precise positions in massive convoys. June 4th brought the first movement orders. Sections of the artificial harbours began moving into the channel, positioned midway across, awaiting the invasion scheduled for June 5th. Then weather intervened. A massive storm system swept across the channel, forcing postponement. The harbour components wallowed in rough seas for 24 hours, while Eisenhower agonised over whether to proceed or delay further. When Eisenhower finally ordered the invasion to proceed on June 6th, the harbour components were already at sea. In the pre-dawn hours of D-Day, while Allied soldiers stormed ashore under withering fire, the first elements of the artificial harbours were being towed into position. The operation proceeded with choreographed precision despite surrounding chaos. The first Phoenix caissons reached positions roughly a mile offshore from both Omaha and Gold Beaches. Powerful harbour tugs manoeuvred the massive concrete structures with remarkable delicacy, nudging them into precise positions marked by buoys laid by naval survey ships. The controlled flooding of Phoenix caissons demonstrated brilliant design. Each caisson contained multiple chambers with individual flood valves. Engineers could flood specific chambers to achieve exact positioning and orientation before settling the structure permanently to the seabed. The process required hours of careful work for each caisson, but results justified the effort. As the Phoenix breakwater took shape, it created sheltered water where ships could anchor safely. Simultaneously, 70 obsolete merchant ships moved into position for deliberate sinking. These vessels, stripped of everything valuable and fitted with scuttling charges, made their final voyage under their own power. At predetermined coordinates off the invasion beaches, crews opened seacocks, detonated charges, and abandoned ship. The vessels settled to the bottom in carefully planned positions, creating an outer line of protection against Atlantic swells. At Omaha Beach, 10 ships went down in precise formation. At Gold Beach, another line of deliberately sunken vessels established the outer perimeter. The scuttling operations proceeded so smoothly that most ships settled within 50 feet of their assigned positions, a remarkable achievement given the complexity of deliberately sinking a ship exactly where intended. The floating roadways came next. Long trains of linked pontoons and bridge spans snaked across the channel, towed by dedicated tugboats. Once in position, Royal Engineers secured them to pier heads and extended them toward shore. The flexible joints that Beckett had designed proved their worth as the roadways undulated with waves while maintaining structural integrity. By June 13th, the harbour at Arromanches had developed sufficiently to provide facilities capable of accommodating 75 Liberty ships and smaller craft simultaneously. The speed of construction astonished even the engineers who had planned it. Within just 7 days of the landings, both artificial harbours were beginning to handle cargo. The first supply ships to use the facilities found themselves in the strange situation of docking at piers that had not existed 10 days earlier in harbours built from materials scattered across England 2 weeks before. Ship captains accustomed to traditional harbours marvelled at the ingenuity. One Liberty ship captain wrote in his log about approaching what charts showed as open beach, instead finding complete harbour facilities, including floating piers, breakwaters, and navigational markers. His ship discharged 400 tons of ammunition, 200 tons of rations, and 150 vehicles in 8 hours. The entire facility floated on the tide, rising and falling 15 feet between high and low water, yet remained perfectly functional throughout. Then disaster struck with devastating suddenness. On June 19th, the worst June storm in 40 years descended on the English Channel. For 3 days, northeasterly winds of force 6 to force 8 pounded the Normandy coast. Waves reaching 8 feet in height crashed against the artificial harbours. The outer breakwaters, designed to absorb such punishment, began to fail. Some broke apart under the relentless pounding. Others tore free from their anchors and drifted into the inner harbours, where they smashed into Phoenix caissons and floating roadways. At Omaha Beach, the American harbour suffered catastrophic damage. The facility had not been fully completed when the storm arrived. Critical reinforcements and anchor systems were still being installed. Phoenix caissons cracked under the wave assault. Floating roadways broke free and washed onto the beach in tangled wreckage. By the time the storm abated on June 22nd, the American harbour was beyond repair. Surveys showed that restoring it would take longer than building it originally, as damaged components would first need to be removed. The American command decided to abandon their harbour. Usable sections were salvaged and sent to reinforce the British harbour at Arromanches. The British facility, more protected by natural geography and more completely assembled before the storm, survived with damage but remained functional. It was substantially reinforced with units salvaged from the American harbour. Phoenix caissons were pumped full of sand to provide greater stability, a measure that undoubtedly explained why the British port continued operating far beyond its design life. The storm validated the harbour concept even as it destroyed one facility. At Omaha Beach, where the harbour lay in ruins, the breakwater created by deliberately sunken ships had held firm. Vessels anchoring in the protected water behind these block ships rode out the storm with minimal damage. Without even that basic protection, the June storm would have scattered the invasion fleet and potentially doomed the entire operation. The loss of the American harbour forced reliance on direct beach landing of supplies, a technique refined to unexpected levels of efficiency. By early July, Omaha Beach was handling 12,000 tons daily, despite lacking a harbour, an achievement that surprised everyone. Yet this success depended on the breakwater of sunken ships, which was itself a harbour component. The British harbour at Arromanches continued operating long past its design life. Engineers had intended the facility to function for just 3 months, sufficient time to capture and restore Cherbourg. Instead, the harbour remained operational for 10 months after the invasion. Through this single artificial harbour passed 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. At peak efficiency, the harbour was landing 7,000 tons of equipment and supplies daily. The facility operated around the clock, with ships docking at any hour to discharge cargo. The floating roadways proved their worth beyond anyone's expectations. Designed for a 3-month lifespan, they handled traffic constantly for 10 months. Fully loaded trucks drove from Liberty ships anchored offshore directly onto French soil across bridges that floated on the tide. Many of these bridge spans found second lives after the war, repaired and used to replace bombed bridges across France, Belgium and the Netherlands. Examples remain visible to this day, including spans over rivers in Normandy and along the Moselle. The German reaction to the artificial harbours revealed complete failure of their military intelligence and strategic thinking. German commanders had based their entire defensive strategy on the assumption that Allied forces would need to capture a port immediately. Rommel had fortified Cherbourg, Le Havre, and other harbours precisely because he believed invasion forces could not survive without them. The Atlantic Wall, with its millions of mines and thousands of concrete bunkers, was positioned primarily around port facilities. When Allied forces came ashore on beaches rather than ports, German intelligence initially interpreted this as evidence of a limited raid rather than full invasion. Even when the scale of the landings became apparent, German commanders assumed the Allies would rapidly move to capture Cherbourg. The appearance of artificial harbours off the invasion beaches shocked the German High Command. They had no intelligence warning of the project despite its massive scope. The concept violated German assumptions about what was militarily possible. Albert Speer, the Reich's Minister of Armaments and War Production, would later provide the most eloquent testament to the harbour's impact. After the war, during interrogation and later in his memoirs, Speer reflected on the Atlantic Wall's failure. To construct defences in 2 years, Germany used 17 million cubic metres of concrete and 1.2 million tons of steel. A fortnight after the enemy landings, this costly effort was brought to naught by an idea of simple genius. The simple genius Speer referenced was the artificial harbour concept. Germany had invested enormous resources into fortifying every port along the Atlantic coast. The Reich's High Command believed these fortifications made invasion impossible without catastrophic Allied casualties. Instead, the Allies simply bypassed the fortified ports entirely, bringing their own harbours with them. This represented more than tactical surprise. It demonstrated a fundamental difference in how the two sides approached warfare. German military thinking remained rooted in 19th century concepts of fortress warfare and defence of strong points. The Allies embraced innovation, willing to attempt solutions that conventional wisdom deemed impossible. The contrast extended beyond the harbours to encompass Allied strategy as a whole. While Germany relied on static defences and counterattacks with armoured reserves, the Allies developed specialised equipment to overcome obstacles. Modified tanks for clearing mines, bridge-laying tanks for crossing obstacles, amphibious tanks for swimming ashore all epitomised this innovative approach. The Germans possessed technical brilliance, as evidenced by weapons like rockets and jet aircraft. But they lacked the industrial capacity and strategic flexibility to turn technical innovations into war-winning advantages. The Allies, particularly Britain and America working together, combined innovation with industrial mass production. The harbours exemplified this combination. Engineering innovations from flexible roadways to controlled flooding systems represented cutting-edge design. Yet the project succeeded because British industry could manufacture these innovations in quantity despite 4 years of total war. Over 45,000 workers contributed to harbour construction. Commercial firms across Britain diverted resources from other war work to produce components. The scale of coordination required dozens of government ministries, military services, and private companies to work in unprecedented cooperation. This organisational achievement matched the technical accomplishment. Consider the Phoenix caissons alone. Building 213 massive reinforced concrete structures, each weighing thousands of tons, required more concrete than most nations produced in an entire year. Construction sites had to be created from scratch along riverbanks. Raw materials had to be allocated despite desperate shortages. Transport to assembly points required specialized equipment and careful scheduling. Quality control had to ensure every caisson could survive ocean towing and storm conditions. The towing operation itself deserves recognition as a maritime achievement. Moving 600,000 tons of concrete and steel across 30 miles of open water while maintaining precise positioning and timing stretched naval capabilities to their limits. The 150 tugs involved represented a significant portion of Britain's entire tug fleet. Many were commercial vessels pressed into military service. Crews received minimal training on towing oversized loads through minefields and enemy-controlled waters. Yet the loss rate during cross-channel towing operations remained remarkably low. Only a handful of Phoenix caissons were lost during transport, and most of those were damaged in the June storm rather than during actual channel crossing. Personal accounts from Royal Engineers who operated the harbour in France provide ground-level perspective on the achievement. One sapper wrote to his family in July 1944, describing 18-hour workdays keeping the facility operational. The harbour lived and breathed like a great mechanical beast. With each tide, the entire structure rose 15 feet and fell again. Workers constantly adjusted moorings, inspected pontoons for damage, repaired roadway sections, and guided ships to pierheads. German artillery occasionally shelled from inland positions. Luftwaffe raids occurred nightly, yet supplies flowed without pause. One day alone saw 40 ships unloaded, carrying tanks, ammunition, rations, fuel, and medical supplies. Merchant Navy crews who used the harbour expressed astonishment at what engineers had accomplished. One captain with 20 years' experience wrote that the facility appeared as substantial as any permanent installation he had docked at during his entire career. The engineering required to create this from nothing, to anchor it against channel tides and storms, and to maintain it under combat conditions represented an achievement that would be studied for generations. His ship discharged 500 tons in 6 hours and departed to make way for the next vessel. The efficiency rivaled peacetime operations at established ports. The impact on the Normandy campaign's outcome cannot be overstated. Without the harbours, the Allies would have faced 3 choices, all dire. First, accept massive casualties capturing a fortified port like Cherbourg immediately after landing, when forces were weakest and German resistance strongest. Second, rely entirely on beach landings for supplies, exposing the invasion fleet to weather that could destroy the entire operation, as the June storm demonstrated. Third, delay invasion indefinitely while seeking an alternative that might not exist. The harbour solution eliminated these impossible choices. It provided capacity equivalent to a major port without the casualties of assault or the vulnerability of open beaches. The facilities handled sufficient tonnage to sustain the build-up of forces in Normandy during the critical first months. By the time Cherbourg fell to American forces on June 26th, the immediate crisis had passed. The Allies had established an unshakable foothold in France. Even when German demolitions left Cherbourg unusable for weeks, the advance continued because the harbour at Arromanches maintained supply flow. The strategic implications extended beyond Normandy. The success fundamentally altered Allied amphibious doctrine. After the invasion, planners no longer assumed they needed to capture a port immediately. Future invasions could land on any suitable beach, knowing that artificial harbour techniques could sustain operations until permanent ports were captured and restored. This flexibility gave enormous advantage in choosing landing sites. Beaches could be selected based on defensive weakness rather than proximity to ports. German commanders could no longer concentrate defences around harbours, knowing the Allies might land anywhere along thousands of miles of coastline. The paranoia this induced forced Germany to spread forces thinly rather than concentrating them at decisive points. Plans were drawn up to use harbour technology for the eventual invasion of Japan. Engineers were dispatched to the Pacific to survey potential landing beaches and assess construction requirements. The atomic bombs dropped on Hiroshima and Nagasaki in August 1945 rendered these plans moot, but the preparation demonstrated how thoroughly the concept had been embraced as standard Allied procedure. No similar wartime engineering feat has been attempted since 1944. The combination of technical innovation, industrial-scale production, absolute secrecy, and operational deployment under fire remains unique in military history. Modern militaries studying amphibious operations still examine the artificial harbours as a case study in solving impossible problems through engineering ingenuity. Physical remains survive to this day at Arromanches. Phoenix caissons, still visible at low tide, mark the outer breakwater. Local fishermen use them as landmarks for navigation. Tourists visiting the invasion beaches can see concrete evidence of what Allied engineers accomplished in 1944. Several Phoenix caissons dot the British coastline as well, monuments to construction problems and testing failures. At various locations along the English coast, caissons that sank during towing or broke up in storms lie as scheduled historic monuments, accessible at low tide for those willing to examine their construction. These failures, preserved accidentally as monuments, remind us that the project involved considerable risk. Not every component performed as designed. Not every caisson reached France intact. The June storm destroyed one complete harbour and damaged the other. Yet the project succeeded because engineers had built in redundancy, created multiple solutions for critical problems, and adapted quickly when initial designs failed. The long-term impact on civil engineering deserves recognition. Innovations developed for military necessity found peacetime applications. Floating bridge technology advanced significantly. Post-war harbour construction incorporated lessons learned about breakwater design and tidal accommodation. Concrete mixing and curing techniques developed to produce the Phoenix caissons under wartime pressure improved commercial construction practices. Perhaps most importantly, the project demonstrated that massive engineering undertakings could be completed in months rather than years when urgency demanded. The organisation, planning and execution skills developed during harbour construction influenced post-war infrastructure projects worldwide. Personnel involved in building the artificial harbours dispersed after the war into commercial construction, bringing with them experience in managing complex projects under severe constraints. Recognition came slowly. Wartime secrecy kept details classified for years after 1945. The engineers themselves, modest by nature and training, rarely sought publicity. Only decades later did historians begin recognizing the scale of achievement. The institution of civil engineers included the artificial harbours among projects celebrated during its 200th anniversary. Scholarly studies examined technical and organisational aspects. Documentaries brought the story to wider audiences. Military historians acknowledged that invasion success depended as much on engineering innovation as military valour. The contrast between Allied and German approaches to the invasion problem crystallized in the harbours. Germany chose the obvious solution: fortify ports so heavily that capture becomes impossible. The Atlantic Wall, with its millions of tons of concrete and elaborate defensive systems, represented conventional military thinking applied with German thoroughness. The Allies chose the unobvious solution: make ports irrelevant by creating new ones where needed. This required believing the impossible could become possible through engineering and industrial effort. It required leaders willing to authorize enormous expenditures on an unproven concept. It required engineers willing to attempt what their training said could not be done. It required construction workers toiling in ignorance to build components they did not understand for purposes they could not imagine. The difference in mindset explains why the Allies won. German military culture valued obedience, hierarchy, and adherence to proven methods. This produced excellence in execution, but rigidity in planning. When Allied actions violated German assumptions, the command structure struggled to adapt. Allied military culture, particularly Anglo-American cooperation, valued innovation, flexibility, and pragmatic problem-solving. This sometimes produced chaos and inefficiency, but it allowed rapid adaptation to changing circumstances. When conventional solutions proved inadequate, Allies sought unconventional alternatives. The harbours embodied this cultural difference. A German general presented with the harbour problem would have calculated forces needed to capture Cherbourg and accepted the casualties. An Allied general authorised building floating cities to bypass the problem entirely. On the 40th anniversary of the invasion in 1984, a group of surviving harbour engineers gathered at Arromanches to reflect on their achievement. The reunion included British and American participants, military and civilian contributors, designers and construction workers. Their reminiscences provide a fitting conclusion to the story. One engineer who supervised much of the construction spoke at the reunion dinner. They were young men facing an impossible task. Build a harbour that can be assembled in days, that can float yet withstand Atlantic storms, that can handle more cargo than Dover while anchored to sand rather than bedrock. Every engineering principle they had learned said it could not be done, yet they had no choice. The invasion depended on solving these impossible problems, so they stopped thinking about why it could not work and focused on making it work. They tested, failed, modified, and tested again. They manufactured on a scale that strained Britain's industrial capacity. They towed floating concrete boxes across mined waters. They assembled harbour components while German artillery shells fell around them. And it worked, not perfectly. One harbour was lost in the June storm. Many components failed. Constant repairs were needed, but it worked well enough. The harbour kept supplies flowing. It bought time to capture Cherbourg. That time made the difference between victory and defeat. Alan Beckett, whose roadways had proven crucial, offered his perspective. He was a young lieutenant when assigned to solve the floating roadway problem. The requirements seemed contradictory. Must be flexible enough to accommodate 15-foot tidal variations. Must be rigid enough to support loaded trucks. Must be durable enough to last months in salt water. Must be simple enough to manufacture quickly. Must be transportable across the channel. Each requirement alone posed significant engineering challenges. Together, they appeared insoluble. He spent weeks sketching designs, building small models, testing them in laboratories. The breakthrough came from watching a snake move across sand, its body flexing at multiple points while maintaining overall forward motion. He realized the roadway needed similar characteristics, rigid within each span, but flexible at the joints. The torsional flexibility proved to be the key innovation. Once that principle was established, detailed engineering followed. Seeing the roadways still functioning at Arromanches 10 months after the invasion, handling traffic far exceeding their design capacity, gave him greatest satisfaction of his engineering career. A construction manager who oversaw caisson production recalled the challenges of obtaining materials in wartime Britain. Everything was rationed. Cement, steel, timber, labour, transport. Everything was needed for a dozen other urgent priorities. Yet the project received what it needed because Churchill and Eisenhower understood its importance. The coordination required was staggering. Concrete had to be mixed to precise specifications. Steel had to be fabricated and positioned within millimetre tolerances. Caissons had to be built in dry docks created from scratch along riverbanks. Then they had to flood the dry docks, float out multi-thousand-ton concrete boxes, and tow them to assembly points without structural failure. That they accomplished this at dozens of locations simultaneously, while maintaining absolute secrecy, while German bombers raided nightly, spoke to the determination of everyone involved. From the humblest labourer to the most senior engineer, everyone understood they were building something that would change history's course. A Royal Navy officer who commanded one of the tugs towing Phoenix caissons across the Channel shared his memories. The crossing took 2 days at maximum safe speed of 4 knots. They towed a large caisson weighing over 6,000 tons. The tow cable was thick as a man's arm, yet he watched it stretch tight with the strain. They navigated through mine-swept channels marked by buoys that enemy boats tried to remove. They maintained station in a massive convoy while avoiding collisions with other tows. The entire channel was filled with ships, thousands of them, all heading for Normandy. When they reached their assigned position off Omaha Beach, they held station while engineers flooded the Phoenix in a carefully controlled sequence. It took 6 hours to sink that massive caisson into precise position. Then they cast off and returned to England for another tow. His crew made 4 round trips in 10 days. They were exhausted, running on tea and determination, but they never questioned the importance of their work. The reunion concluded with a visit to the beaches where the harbour had stood. The participants, now elderly men, walked across sand where artificial harbour components had once created a bustling port. Phoenix caissons offshore marked the ghost of what had been. Some of the engineers wept, remembering comrades who had not survived the war, thinking about the magnitude of what they had achieved in 1944. One participant summarized the feelings of all present. They succeeded beyond their own expectations. The harbour worked, supplies flowed, the invasion held. They helped win the war. Looking back across 4 decades, he felt immense pride in what they accomplished. They proved that engineering ingenuity, industrial capacity,